Hey, we're Team 7. My name is Matthew. I'm the team leader, and I did the power electronic simulations.
My name is Chris, and I was the solar cell specialist.
My name is Jacob Wenzel. I was PCB support and report specialist.
I'm Jonathan. I did the microcontroller programming and the PCB soldering.
I'm Lucas Therian, and I was the PCB designer and supply chain manager.
In regards to the communication tools that we used Discord as well as various text messages to communicate meeting times for us to meet and work on different assignments.
All right, the PCB we were tasked with designing was a Hall effect sensor that consisted of two parts. An instrumentation amplifier for detecting voltage, and a current sensor brought to you by the good folks who brought you the Javelin Texas Instruments. The board design itself was a fairly compact design inspired by the enormous amount of tunnels I use in city skylines. All right, after the PCB was designed, we sent the art files to a company called JLC PCB who manufactured them in China.
So the specifications we were given for the PCB were we needed a 0 to 3 volt output on all of the sensors. We had a maximum current input of 10 amps, and the voltage input had to be between negative 50 volts and 50 volts. So based on these specifications, we calculated the values for the resistors and the capacitors that we needed through multisim. We then put all of those into a bill of materials. We determined also that all of the resistors and capacitors had to be of size 0805, and then we ordered all of them through DigiKey.
Before soldering any components, the bare PCB was probed for any shorts. There were none found. After this, the components were soldered to the PCB using special solder paste ordered for the resistors and capacitors. The integrated circuits, power lugs, and 6-pin connector were also soldered. They were measured with a tabletop multimeter and the oscilloscope to ensure everything was functioning and any defects or inconsistencies were found. The voltage and current sensors were then tested, again with the oscilloscope, and were found to be functioning correctly.
Using the steps provided in Lab 5.1, 5.2, and 6, along with the instructions laid out in the G02 reference documents, all the necessary drivers, software, composers, and add-ons were installed to the testing computer. Following this, the microcontroller was programmed within MATLAB, specifically Simulink, and this code built upon itself up until the final project, where modifications were made to our PI loop in order to achieve a very stable and clean output. One difficulty faced during the testing process was the external hardware communication with the microcontroller was not working completely at first. However, through some error debugging, the issue was found to be that the board could only communicate serially, and we were using serial XCP at first, but once this was fixed, we had no issues at all.
With our PCB, microcontroller, and hardware all set up, here's a clip in lab with the results running in real time on the oscilloscope. Hey, we're Team 7. This is our final project. So what we're doing is a DC to AC converter. So it takes the current and voltage from this power supply, puts it into the PCB where it steps it down in order for the microcontroller to read it. And then from the microcontroller, you add a DC power supply, and you can create it into an AC waveform. So essentially DC power to AC power. So let's take a deep dive into our hardware. So first we have our Simulink code used from previous labs. And then you can move that into our microcontroller, which is connected to the power console. And the power console was already set up for us. And then from there we have our PCB design. And then we also have our DC power. And then that's our oscilloscope. So one key thing that you can see from it is that you can change the reference current in real time to change the output. So if we change it from 0.5 to 1.5, you can see the jump. So that was our final project. This has been Team 7's video for the DC to AC converter. Thank you for watching. Make sure to like and subscribe. You guys want to add anything?
Nope.
Nope, that's
We're
it.
good.
All right. This is our final project.